Greetings. My name is Tom Fay, and on behalf of the Aircraft Engine Historical Society, I'd like to present a technical description of the Ratier hollow-bore constant-speed aircraft propeller. This propeller design allowed a cannon to be fired through the open bore of the propeller hub. I'll take this early opportunity to apologize for my Midwestern American attempt at speaking the French language and for any errors in translating the French documents via Google Translate. In his earliest days, Frenchman Paulin Ratier was a carpenter, and he founded his company in 1904 to produce cabinetry. As a licensee, Ratier began producing Rapid brand aircraft propellers in 1910. He went on to build propellers for Breguet, as well as propellers of his own design. To survive the many economic slumps of the first third of the 20th century, Ratier used its diverse technical and engineering expertise to produce all kinds of devices, mechanical components, vehicles, and wooden assemblies, but they always kept their hand in aviation. Ratier and his company have a fascinating history, all very well documented at ratier.org. The first aircraft to use a motor cannon, a 37mm cannon no less, was the SPAD-12 in 1917. But the first aircraft with the Ratier hollow-bore propeller was the Moteur 406, which flew in prototype form as the MS-405 in 1935. This recent photograph is of a licensed copy of the MS-406 produced in Switzerland during World War II and designated the D3801. The 406 is of mixed construction, using an aluminum framework with an interior of the aft fuselage stabilized with wires and turnbuckles, all covered in fabric. Other panels, particularly in the forward fuselage, were made of an aluminum wood matrix called Plymax. The aircraft had the motor cannon, a retractable radiator, and its first flight was in December of 1938, after which it was accepted immediately into service. The MS-406 used 4 different propellers over the course of its service life, and those are listed below. For the purposes of this video, only the Ratier 1607 will be discussed. Of note on the aircraft in the center panel is the retractable radiator. This radiator could be raised or lowered to reduce drag while meeting the cooling demands of the engine. The MS-406 was powered by the supercharged Hispano-Suiza V12 engine of 36-liter displacement. It was a 60-degree bank configuration with shaft-driven, single overhead cam that operated 2 valves per cylinder. The head and cylinder block was one piece, and articulated connecting rods were used instead of fork and blade configuration. You'll notice both the intake and exhaust ports are on the outside face of the cylinder banks, and it is this configuration, as well as the hollow shaft of the large diameter reduction gear, plus the availability of a modern, constant speed, hollow bore propeller that allowed for the motor cannon. You can see the 3 Solex carburetors being fed directly by the gray pipes running forward from the supercharger, and the 6 red exhaust ports. This rendering shows the configuration of the Hispano-Suiza model HS404 20mm gas-operated cannon installed on the crankcase of the Hispano-Suiza 12Y engine. The large drum holds 60 rounds of ammunition. This is a view from the rear of a 12Y engine looking forward through the trough between the cylinder banks. The cannon runs through this trough with the barrel extending through the hollow reduction gear shaft. This is a view of a 12Y engine from the rear showing the cannon installed. Hispano 404 Canon, shown here, was an impressive weapon able to fire 600 rounds per minute. As compared to the Browning M2 50 caliber machine gun, shown in red, the 404 had a similar rate of fire and maintained 90% of the muzzle velocity of the Browning machine gun, but with a projectile weight almost 3 times that of the M2. Here is what the Ratier 1607 propeller looks like underneath the spinner. Note the slip rings on the rear of the propeller with a conduit running forward to the electric motor up front. The 12Y-31 engine in the 406 generated a maximum of 848 horsepower and drove a 10-foot 2-inch diameter propeller. Fortunately, the Ratier website had a wonderful color rendering of the 1607 type propeller, which will guide the explanation of its mechanics. We'll go through the propeller one color at a time. The upper left quadrant of this layout drawing shows a side view of the propeller with a 24-volt electric motor at the front, followed by the reduction gear assemblies, and ultimately the hub with the blade's pitch-changing linkages. This propeller makes extensive use of worm gear trains in the reduction system. The propeller is designed to operate between 28 and 48 degrees of blade pitch angle, so a 20-degree range. It is a rather narrow range of operation, as we'll soon see. A single aluminum propeller blade weighs 41 pounds, and the complete prop on the nose weighs 277 pounds. An additional 10 pounds of fuselage-mounted ancillary equipment raises the installed system weight to 287 pounds. The reduction ratio is 4,200 turns of the motor to 1 turn of the propeller, or 248 turns of the motor over 8 seconds to traverse the full 20 degrees of pitch change. This equates to a pitch change rate of 2.5 degrees per second. So how does the 2.5 degree per second pitch change rate of the Ratier propeller compare to other motor cannon propellers of that time period? The answer is somewhere in the middle of the pack. The Chauvier and the VDM electric propellers are the slowest at 1.3 and 1.5 degrees per second, respectively. The Aero Products hydraulic propeller at 5 degrees per second is twice as fast as the Ratier 1607. This has implications for RPM control, especially upon entry into a dive. Overspeeding the propeller means overspeeding the engine, which carries the risk of catastrophic mechanical failure. Also of note on this table is the pitch change range of the propellers. The relatively low-powered, low airspeed MS-406 cannot handle, nor does it require, a wider pitch change range, while the higher performing Cannonbore aircraft, such as the BF-109 and P-39, have larger pitch change ranges and higher absolute pitch change angles. Back to the color cutaway, let's look at the electric motor in the Ratier 1607. First stop is the electric slip ring assembly, which conducts electrical power from the propeller regulator to the motor on the spinning propeller. Shown in the upper right is the slip ring assembly for the Ratier 1607 propeller. There are 5 lanes of conductors on the slip ring assembly. Number 1 is common ground, 2 high current increase pitch, 3 high current decrease pitch, 4 low current increase pitch, and 5 low current decrease pitch. Normal loads on the motor can be accommodated by the low current circuits. If the current draw exceeds the limit set for the low current system, breakers will open, transferring the electric flow to the high current system within 0.15 seconds. This 2 current system plus the electromagnetic brake provide a more efficient and smoother pitch change operation by reducing motor activity, overrunning of the desired pitch set point, and hunting of the blade pitch. Next, let's take a look at the electric motor located at the front of the propeller assembly. The motor assembly is about the diameter of a medium-sized pizza. It runs on 24 volts direct current with a 6-pole field winding, which is the outer windings, and a 6-pole armature, which does the spinning. Because of the mechanical advantage offered by a larger diameter, the motor has high torque despite the modest power that doesn't exceed 1/4 horsepower. Switching polarity to the motor reverses the direction of the motor. On the left is the complete motor assembly showing the output spur gear in purple, which is mounted directly on the armature of the motor. The armature has been removed from the drawing on the right, showing the field windings of the motor. This schematic of a 4-pole motor shows one of the more interesting features of the Ratier motor system. The rotating armature is shown in light blue. Note that there is a separate field coil in red dedicated to perform a braking function. When the propeller is on speed, the motor field windings are not energized. However, the braking field coil and one pole of the armature are energized with low current. This makes the two opposing electromagnetic fields attract each other like a two-magnet jewelry clasp, trying to lock the motor in place. When an off-speed command is received to turn the motor one way or the other, the braking circuit is de-energized. It's a very clever system. This motor braking system helps combat the momentum of the pitch change system and prevent overrunning the signaled pitch command. Next step in the system is the reduction gearing shown in purple. The Ratier 1607 uses a number of worm gears in the reduction scheme, so a short video tutorial produced by 3D Printer Academy will be of benefit. The Google translation from French calls worm gears endless screws, which is both a mechanical fact and a rather pleasant imagery. But I will call the driving component a worm gear and the driven component a worm wheel.
You may have noticed that I have to spin the red handle the exact number of times as there are number of gear teeth on the blue worm wheel. Yes, a professionally manufactured worm drive will have much tighter clearances than this 3D printed model of a worm drive. We could get the blue worm wheel to spin by rotating the red worm gear. However, we can't spin the red gear by trying to spin the blue gear. It completely locks in place.
This is an actual picture of a Ratier worm gear drive system and a good example of how reduction is done in the 1607 propeller. A vertical worm gear number 1, shown with the arrow, spins and rotates worm wheel number 1. The axle for worm wheel number 1 has a worm gear on it, worm gear number 2. Worm gear number 2 spins and rotates worm wheel number 2. So let's walk through the gear path of the Ratier reduction gear train system. Recall that the armature of the electric motor had a purple spur gear attached to it. This is depicted as the purple gear in the middle of this diagram and will be referred to as the driver spur gear. The driver spur gear meshes with a driven spur gear shown at the second arrow. On the shaft of the driven spur gear is a worm gear. That worm gear interacts with a worm wheel. The shaft of the worm wheel has a worm gear at the end of it, and that worm gear interacts with a secondary worm wheel, which will drive the jack screw, which we'll see in a moment. Back to our handy color diagram, we'll now trace the path of the gear train which drives the jack screw. So let's trace the final path in the reduction gear train of the Ratier propeller. Input from the secondary worm wheel of the previous compartment has a shaft at the end of which is a tertiary worm gear. This worm gear interacts with a quaternary worm wheel. In the center of this worm wheel is the jack screw. This orange jack screw is threaded such that when the worm wheel turns, the orange jack screw will either move to the left or to the right. Attached to that jack screw is a blue sliding plate. And attached to that blue sliding plate is the rack. This rack meshes with the segment gears on the base of the propeller blade and turns the blade. All of this runs in grease. There are 3 grease nipples on each hub arm, so 9, plus 3 on the hub. So there are 12 grease nipples to be greased for every 10 hours of operation. So now we've traced the gear train for one of the propeller blades. But remember that this propeller is a 3-blade propeller. The parts count of this propeller, as well as the precision machining and alignment of all the gear train components, is impressive to say the least. Propeller blades are subject to very large centrifugal forces, up to 48 tons of force for a 66-pound propeller blade, and torsional loads are trying to twist the blade towards flat pitch. In addition, there are thrust loads trying to bend the blade forward. Ratier engineered a solution that would offset some of these forces, one against the other, specifically by 1. Using inclined bearing races, essentially a superfine pitch ball screw, which balance the torsion loads trying to screw the blade into the hub with a centrifugal force trying to unscrew the blade at design speeds. Number 2 was canting of the blade socket slightly forward in the hub, which combined with the ball ramp and dynamic forces at design speed, diminished the power requirements for changing blade pitch. Each blade socket for the 1607 propeller has 13 rows of bearings, containing a total of 860 individual balls. This tallies to 2,580 balls for a 3-blade propeller. Each ball is just under 4 millimeters in diameter, or roughly the size of a BB. This large number of balls was required by the necessity to keep individual ball loadings under 110 pounds each. The blade sockets were lubricated with Intava grease, which contained a small portion of fine powdered graphite. So how is a constant propeller speed selected and maintained? The answer is a centrifugal flyweight governor developed initially for steam engines. This is the propeller governor, the speed sensor and speed controller of the propeller engine combination. It is mounted on the engine and driven by the engine at half engine speed. The 2 blue flyweights will pivot outwards under centrifugal force. As the tops of the flyweights pivot outwards, the bottom arms move upwards, raising the red actuator rod. The rod will displace the center electrical contact upwards and complete a circuit that energizes the increased pitch circuit. As the propeller blades increase in pitch, with a constant throttle setting, the engine will slow. The flyweights, in turn, will migrate back towards their starting position and deactivate the increased pitch circuit, and vice versa. When the system is at the selected speed, termed on speed, neither contact is activated. The motion of flyweights is moderated by the speeder spring that surrounds the actuator rod. Through the rack and pinion assembly, the pressure on the speeder spring can be adjusted by the pilot. Increasing pressure on the spring will make it harder for the flyweights to move outward, Thus, a higher engine set speed will have been selected, and vice versa. So now we know the mechanics of the propeller control system, but how does the pilot control those functions? Shown here is the pilot half of the propeller control system mounted in the cockpit. The propeller mode switch is located towards the middle of the diagram, and it can be set in automatic, stop, or manual. In automatic mode, propeller control is managed by the propeller governor. When the mode switch is in stop, the propeller governor is inactivated and only the propeller brake is energized. When the mode switch is in the manual position, the governor is inactivated and the propeller pitch is managed directly by the pilot using the manual pitch control switch. As an aid to the pilot, when the lower pitch circuit is activated, the green light goes on, and when the higher pitch circuit is activated, the red light is illuminated. Here now is the airframe and propeller mounted half of the propeller control system. In the top part of the diagram are various relays that connect or disconnect circuits as demanded by the pilot or the propeller governor. Because the current involved to drive the motor is too large for the delicate contacts in the propeller governor, solenoid switches are used to close these circuits. The propeller governor, or pilot in the manual mode, activates or deactivates the appropriate solenoids to direct current to the desired circuit. The propeller governor is shown midway in the diagram. It has 3 wires, one for low pitch, one for high pitch, and the common wire which services either circuit. At the bottom is the electric motor on the propeller hub, fed by the 5 wires we've previously discussed. There are high limit and low limit pitch switches that will stop the motor when the limits of pitch have been reached. This diagram shows the electrical schematic of propeller control in its entirety. Just to make things a little more complicated for me to explain, but make it an easier life for the pilot, the throttle and propeller linkage were interconnected. The manual states a mechanical connection is made between the propeller governor and the throttle linkage, which maintains a determined speed for each position of the pilot power lever. Below a certain engine RPM, the interconnect between the throttle and governor is disabled. The interlinkage provides the ideal combination of throttle position and propeller pitch to optimize efficiency. The precise coordination schedule between the throttle and the governor was not described in the manual. With regards to flight operations, for warm-up, the manual mode was used to put the prop in lowest pitch. Once temperatures and checks were made, the propeller was put into automatic mode for takeoff, climb, and level off. While in straight and level cruise condition, it is suggested that the propeller mode be placed in stop to prevent pitch cycling and reduce wear on the propeller components. Descent to landing should be performed in automatic, but on final approach, manual mode should be selected to move the prop to low pitch to assure rapid acceleration should a go-around be required. This drawing from the Ratier manual shows the location of various propeller system components. The electrical cables going forward to the propeller slip ring is labeled number 1. The propeller governor, number 5, is located at the rear of the engine. The power lever is number 12, and the storage battery number 13 is located behind the pilot. Note the extended radiator below the center section of the wing. I realize this image is hard to see in detail, but this is page 1 of the parts that make up the Ratier 1607 propeller. Here are more components of the propeller, and highlighted in the red circle are the 4mm steel balls for the blade retention bearings. Here are a few components magnified to the limits of the document resolution. In the upper left is the brush block containing the 5 rectangular, spring-loaded carbon copper brushes extending like teeth from the assembly. The pitch change rack and segment gear are shown on the upper right, and the ubiquitous worm gears and worm wheels shown below. This rather poignant photograph is that of a French MS-406 pilot killed in 1940 in the north of France. Atop Lieutenant Monti's grave are the remains of the Hispano-Suiza 12Y engine and the Ratier 1607 propeller. From the photograph, it can be determined that this is an early version of the 1607 propeller, as distinguished by, wait for it, a final worm gear drive to change the pitch of the blades instead of the rack to segment gear as detailed earlier. The second aircraft to use the Ratier open-bore propeller was the Dewoitine D520, which first flew in 1938. Approximately 900 of these aircraft were built. The D520 was a much more modern aircraft than the MS-406, with all-metal stressed skin construction. It used the same family of Hispano-Suiza 12Y engines, Hispano nose cannon, and Ratier electric propeller as the 406. Its first flight was in 1938, and it entered service in January of 1940. The D520 used the Ratier Model 1606 propeller, which was very similar to the Model 1607 previously discussed. The Hispano-Suiza 12Y-29 engine in the D520 made 50 more horsepower than the 406 engine, and it drove a 3-blade propeller that, at 9 foot 10 inches in diameter, was 4 inches smaller in diameter than the propeller used on the MS-406. The 1606 propeller had the same 20.5 degree range as the 1607 propeller, but had a lower reduction ratio of 3200 to 1 versus the previous 4200 to 1. This produced a slightly improved pitch change rate of 2.7 degrees per second. The propeller blade, propeller, and installed system weights were very similar to the 1607 propeller. The layout of the propeller components and operation of the propeller system of the D520 is essentially identical to that of the MS-406. I include this drawing mostly as I am struck by its similarity to the Spitfire in this view. I will point out that the famous Royal Navy test pilot, Scotsman Captain Eric Winkle Brown, did not enjoy the flight characteristics of the Dewoitine and found it very sensitive to an aft center of gravity condition. I'd like to circle back now to the MS-406, as there is an interesting curveball to its open-bore propeller history. As a neutral, non-combatant country in World War II, Switzerland had licensed the MS-406 design for local production to support national defense. The resulting aircraft was designated the D3801. Over 200 aircraft were produced by a consortium of companies, and in place of the electric Ratier propeller, the D3801 used a hydraulic, open-bore propeller made by the Swiss engineering firm Escher-Wyss. The Escher-Wyss design used a stationary piston, shown in red, which was affixed to the central tube of the propeller assembly. High-pressure oil from the hydraulic propeller governor was directed to either in front or behind this piston to move the translating cylinder, which is shown in light blue. Pins on the exterior of this translating cylinder were linked in dark blue to the eccentric pins located at the base of the propeller blade. The movement of the cylinder casing fore and aft changed the pitch of the blades. The use of a translating cylinder allowed the actuation pins to be located on the outside of the hydraulic cylinder, which greatly simplified the design. The hydraulic unit of the propeller is shown on the right. Of note in the drawing on the left are the 7 bearing rows, indicating the use of the Ratier patented ball ramp design in the blade root bearings. Since the Escher-Wyss propeller is a hydraulic propeller, there had to be some means to channel high pressure oil from the engine-mounted governor to the spinning propeller hub. The Hispano 12Y engine here on the left has the typical spline propeller shaft of the type used by the Ratier electric propellers used on the MS-406 and the D520. On the right is a Hispano-Suiza 12Y engine that has a flange surface for attaching the propeller assembly. This design provided a larger bore to accommodate the double-walled concentric oil channels required by the Escher-Wyss prop, while leaving sufficient room for the Canon barrel to extend through the bore. The hydraulic propeller governor for the EW V3 propeller is shaded in red, and it is driven by the large propeller reduction gear. 3 lines flow from the governor to the propeller hub. The yellow line is for the high pitch side of the stationary piston. The red line connects to the low pitch side of the piston, and the blue line is one that unlocks an internal pitch lock mechanism that locks the pitch of the propeller in place at all times except during a pitch change command. I should add that the hydraulic governor works very similar to the electric governor, except that the actuation rod moves a spool valve that directs oil flow instead of electricity. As of 2023, the only flying member of the MS-405, MS-406 lineage is a single D3801 aircraft located in Europe. As you can see, the D3801 retained the mixed construction of the MS-406. And more intriguing, the right-hand photo shows the distinctive shaping of the Escher-Wyss propeller hub on the nose of the aircraft. For those with the interest, there are 2 outstanding high-resolution videos of the D3801 in action at the links noted on this page. Amazingly, there were at least 9 manufacturers of motor cannon propellers during World War II. The Hamilton Standard open bore unit was experimental, and while tested and flown, it did not enter production. The other 8 propellers were in production and served in World War II, but those perhaps are stories for another time. For those of you that have stuck around to this very end, I thank you very much for your patient attention. I ask that you consider viewing additional videos on this channel and to visit the Aircraft Engine Historical Society website at www.enginehistory.org. Thank you.